Hello, my name is Yunseok Han from ADAS Lab at Seoul National University. In this seminar, I'd like to discuss a practical concern regarding numerical mismatches in large language model reinforcement learning. As is well known, RL fine-tuning has become a common approach for enhancing the reasoning capabilities of large language models. To apply RL, we first need to collect responses from the model, a process known as rollouts. In practice, modern RL frameworks rely on inference-optimized engines such as VLLM or SGLang to perform these rollouts efficiently. However, this is where an issue arises. While rollouts are performed using inference-optimized engines, model training, that is, updating the LLM parameters, is typically done using training-optimized engines such as Megatron or FSDP, which are designed for efficient gradient computation. Although this may not appear problematic at first glance, these two systems are optimized for different objectives and therefore rely on different computational kernels. As a result, even when using the same model with the identical mathematical groundings, the underlying numerical computations can differ, leading to a training inference mismatch. In this seminar, I will summarize and discuss two papers that address this issue. The first paper from the Quan team provides a theoretical formulation showing that approximating sequence-level rewards with token-level objectives in LLM RL relies on the assumption that this mismatch is small. The second paper from the CAI lab demonstrates empirically that this mismatch can in fact be mitigated by using higher numerical precision. First, let me briefly recap the objective of RL for large language models. We sample a prompt X from the dataset D and generates a response Y from the target policy pi theta. Our goal is to maximize the expected reward R under this policy. However, in practice, it is often difficult to perform rollouts directly from the training policy. Instead, we collect responses from a more accessible rollout policy and correct for the result bias using importance sampling. Importance sampling allows us to estimate expectations under a target distribution by sampling from a different distribution and re-rating the samples by the ratio of their probabilities. This provides an unbiased estimator of the target expectation. Furthermore, for autoregressive language models, we can exploit the chain factorization of the sequence probability and decompose the probability of the full sequence Y into a product of token-level probabilities. This allows us to derive a token-level objective. The paper by the QN team views the token-level objective as a first-order approximation of the sequence-level objective. Specifically, they assume that the importance ratio at each token is close to 1 and can be written as 1 plus delta t, where delta t is small. Under this assumption, the sequence-level importance ratio, which is the product over tokens, can be expanded as a product of 1 plus delta t terms. Using a first-order approximation, this product can be expressed as 1 plus a sum of delta t up to second-order error terms in delta t. Ignoring these higher order terms, the, the sequence level importance ratio becomes a sum of terms that do not depend on the model parameters data. Substituting this approximation into the gradient of the sequence level objective, one can show that the summation term cancels out during differentiation, and the resulting expression reduced to the gradient of a token level objective weighted by the token level importance ratios. However, most importantly, this theoretical justification for approximating the sequence level objective with a token level one holds under the assumption that the mismatch should be small. To better understand this mismatch, we can introduce the training rollout policy pi theta old, which is the LLM with a past parameter theta old, and decompose the original importance ratio into a product of two ratios. The first ratio compares probabilities computed under the same rollout policy but using different computational engines. This term captures the training inference discrepancy. The second ratio compares two different policies evaluated under the same training engine and therefore reflects policy stateless due to delayed parameter updates. As discussed earlier, the training inference discrepancy refers to numerical differences between the training and inference engines. These differences arise because the two different engines are using different computational kernels, or because some batch invariant kernels are disabled to maximize throughput during inference. Policy stainless, on the other hand, arises because the parameter updates delayed. And this gets worse in practical reinforcement learning, since we often generate a large batch of rollouts once and then split it into multiple mini batches for several gradient updates. As a result, the responses are sampled from a policy that is far updated relative to the current parameters, which amplifies the mismatch. While we do not focus on this seminar, the mismatch can be further serious in mixture of experts models. In such models, different numerical computations may trigger different experts, causing the conditioning experts in each importance ratio to diverge and masking the problem more complex. Let's now turn to the second paper, which proposes a way to address the training inference mismatch. In principle, one could consider algorithmic corrections or explicit engineering alignment between training and inference. However, this paper argues that a simple single code line change using float point 16 instead of commonly used b plus 16 can significantly mitigate the problem. As mentioned earlier, we do not sample directly from the target policy pi, but instead sample from an inference policy mu and correct the resulting bias using importance sampling. A key point to clarify is that in standard GRPO algorithm, the importance ratio is primarily used to correct for the bias introduced by differences between the current and previous policy, that is, policy stainless in mentioned the QM team. While an inference engine is typically used to generate rollouts, the numerical discrepancies introduced by the inference engine itself are not explicitly corrected. Naturally, it is possible to introduce an additional importance sampling correction to account for both bias simultaneously. However, doing so would require some additional sampling from the rollout policy under the training engine, which incurs extra computational burden. There are some techniques that apply additional importance sampling at a token and sequence levels to obtain a less biased gradient estimate. One approach is truncated importance sampling, which clips the token level importance ratios by some upper bound. Another approach is masked importance sampling, which masks out sequence whose sequence level importance ratios exceed a threshold. Before discussing the empirical results, let me briefly revisit numerical precision. Although both plot point 16 and B plus 16 use 16 bits in total and therefore have the same memory footprint, they allocate these bits differently between the exponent and mantissa. Plot point 16 allocates more bits to the mantissa, which gives it a higher numerical precision but a narrow dynamic range. In contrast, B plus 16 allocates more bits to the exponents, which gives it a wider dynamic ranges, yielding a range similar to plot point 32, but at a cost, mantissa precision is lower. There are two key reasons why plot point 16 can be particularly effective for RL fine-tuning. First, when using B plus 16, subtle numerical differences introduced by CUDA kernel optimizations or some parallel execution strategies can lead to small errors in token level importance ratios, which then accumulate over time. Second, since LLMs are typically pre-trained using B plus 16, their weights and activations already lie within a stable dynamic range, making the wider exponent range of B plus 16 less critical during fine-tuning. To empirically validate the effectiveness of plot point 16, the authors present 4 figures illustrating how plot point 16 reduces this mismatch. The first 2 figures show scatter plots that match token probabilities recorded under the inference policy and the training policy across multiple runs. Points closer to the identical line indicate smaller mismatch between the 2 policies. As we can see, using plot point 16 significantly reduces this discrepancy. The third and fourth figures plot the difference in sequence level probabilities assigned by the 2 policies into the same sequences. These values are shown on a log scale, so the values closer to 0 indicates that the 2 policies assign similar probabilities to the same sequences. The figures show that when using B plus 16, these differences grow as the sequence length increases, whereas with plot point 16, the difference remains small even for the sequence as long as 25K tokens. Next, to perform a sanity check on several commonly used RL algorithms, the author constructs a dataset with the following procedure. They start from a reasoning dataset such as AME 2024 and assume that for problems that are neither too easy nor too hard, a reliable RL algorithm should in principle be able to achieve close to 100% accuracy. Based on the performance of the QM3 model on this dataset, they filter out the top 20% easiest problems and the bottom 20% hardest problems and conduct their experiments on the remaining subsets. First, The authors compare several existing algorithmic correction methods. The experiments are conducted using the DeepSeek R1QN 1.5 billion model with an 8K context length and evaluated under two RL frameworks, VRL and OAT. Unless stated otherwise, all results are reported under this setting. The results shows that GRPO and its correction variants trained with B plus 16 consistently underperform a simple correction based on F plus 0.16. In particular, the models trained with plus 0.16 achieve higher rewards across both RL frameworks, and their accuracy is either higher or more stable, whereas other methods often collapse or perform worse. The last two figures analyze the mismatch between the training and inference policies during training, measured by the KL divergence and the minimum and maximum probability differences. In all cases, plus 0.16 exhibits a smaller mismatch than the B plus 16 based alternatives. The next figure reports results where all methods are run with plus 0.16 precision. Under this setting, all methods achieve very similar performance regardless of specific algorithm, highlighting that numerical precision plays a more critical role than the choice of algorithm in this setting. Finally, the authors report an ovulation study over different precision settings for training and inference. They find that using B plus 16 for training engine and either B plus 16, plus 0.16, and 32 for the inference engine consistently underperform the configuration where both training and inference engines using plus 0.16 in terms of reward, accuracy, and mismatch. Using plus 0.32 for inference yields somewhat comparable performance, but as expected, it significantly increased the rollout time. Moreover, while plus 0.32 reduces the mismatch compared to other mixed precision settings, it still exhibits higher mismatch than the fully plus 0.16 configuration. To conclude, in LLM RL, there exists a numerical mismatch between the training and inference engines. Also, the second paper empirically shows that the numerical precision can play a more important role than the choice of algorithm in addressing this issue. Of course, I'm not an expert in kernel optimization, but if possible, a more fundamental solution might be to develop some computational kernels that jointly optimize both rollout generation and gradient computation, rather than treating them as a separate systems. This is something I personally became aware of while preparing this seminar, but if this mismatch indeed is a serious issue, it could have implications that not only for LLM RL, but also for LLM deployment for more broadly. If numerical difference between the training and inference engines are large enough to affect model behavior, then we may end up develop and evaluating models under one system while deploying them under another, and this gap could cause the models to behave differently in real-world settings than what we observe during training. It is also plausible that this mismatch is even more pronounced in diffusion language models. Unlike autoregressive models, diffusion language models do not omit a tractable likelihood, and they rely on bidirectional attention, which leads to different computational patterns such as KV cache recomputation or some parallel decoding. If these components behave differently during training and inference, the resulting mismatch could be even more severe than the autoregressive case. So this is it. Thank you for the attention throughout my seminar about the numerical mismatch in LLM RL. If you have any questions or would like to discuss any aspects of today's presentation further, please feel free to contact me anytime via the email shown on the slide. Thank you.